Welcome back to another video. In our last video, we introduced the idea of revealed preference and random utility models, and we used restaurant choice as an example. And we saw that having aspects of the choice decision be unobservable to us as researchers forces us to think about choices as being probabilistic. Today, we're going to explore another fundamental property of discrete choice models, and that is that only differences in utility matter and that the scale of utility doesn't matter. And this is going to have important implications for what we can and can't infer from data on observed choices. Let's jump into some slides to explore this idea further. We have in equation 1 the utility maximization condition that we talked about in the previous video. It just says that if we chose option J, then it must have had higher utility than any of the other options available. So we introduced this probability also in the previous video, but we can take it one step further and actually think about what the probability represents mathematically. So we're taking this utility maximization condition and we're converting it to a probability because we can't see the epsilons, and so we need to think about utility as being probabilistic. Well, what is a probability? Well, it's an integral over an indicator function that the event that the probability is expressing is true or actually occurred. And then we also have to multiply by the density function of the distribution of this variable. And in this case, it's important to emphasize that this is a j-dimensional integral. So there's actually multiple integral signs here, and we're just expressing one in order to simplify the discussion. So that might be a lot to chew on, but we'll break it down in this video and in following videos. One thing we need to know is that just by nature of this utility maximization, a couple of things are going to be true. If I add the same amount of utility to every option, that's not going to change my choice because the choice is relative, it's not absolute, because preferences are ordinal, not cardinal. So if I give every option a 10-cent price discount and everything else is the same, that's not going to change the outcome or the choice that was made. And then another thing is that if I multiply by a positive number, it's also not going to change any of the orderings. So these are two fundamental limitations that are really imposed just by virtue of us having this system of inequalities that is determining the conditions for the choice being made. Okay, so given that I have these two things that I can't get around, how is that going to limit me? And the limitation comes in that only differences in utility matter, and we need to scale the variance of epsilon. So these are called the location and scale normalizations, and these are just basically going to restrict the amount of information we can get from a set of observed choices. So let's go through an example. We can think of maybe Thai food versus Mexican food, and we want to put in a variable for if the person is tall. So maybe taller people like eating at a Thai restaurant. I don't know why that would be the case, but just for the sake of example. And then we have something else. So maybe this is a variable about like, do you speak the language of the restaurant? So do you speak Thai is maybe a dummy variable in X. And then maybe Z is the price of the food that you would eat. So Z is going to be different across the two restaurants. Whether you speak Thai is going to be the same because it's about the decision maker, not the restaurant. And then we also want to try to recover a coefficient alpha in front of whether you're tall or not. So because only differences in utility matter, we have to subtract UI2 from UI1. And what that's going to do is that's going to cancel out these two alpha times tall terms. And so we're going to be left with the difference in the betas times X plus gamma times the difference in the Z's. So we're not going to be able to tell whether tall people are happier than short people, but we can tell if they more strongly prefer one option over another. So if the good is an airline seat with more legroom versus an airline seat with less legroom, then we might find that taller people are more likely to choose the seat with more legroom. The other implication of differences in utility mattering and not absolute levels of utility is that we can only get differenced coefficients on anything about the decision maker. So anything that doesn't change with the choice alternative, we're only going to be able to get differenced coefficients on that. And then the third implication is that we're only going to be able to get an estimate on something about the choice alternative if that thing varies across alternatives. So if every restaurant had the same price, I wouldn't be able to infer how price sensitive the decision maker is, because there wouldn't be any variation to tell me how much they care about the price. So hopefully these things make intuitive sense to you, but they are important formalities that we need to cover before we go further. So once we impose this differences in utility condition, now we're going to have, instead of a j-dimensional integral, we're going to have a j-1 dimensional integral. And then the differenced epsilons, we can just put a tilde over it. And then this is our new formula for choice probabilities. And we've just defined epsilon j tilde as being the difference between epsilon j and epsilon capital J, where we called capital J the reference alternative. But we can choose any option in the choice set to be the reference alternative. That's not going to be a problem. Usually, people will default to have option 1 be the reference or option cap J to be the reference. Now, let's talk about the scale normalization. So because we have to normalize the scale of utility, we can never estimate the variance of the distribution of epsilon tilde. So this contrasts with regression models, linear regression models, where we always are estimating the mean squared error or the root mean squared error. And because of this, our coefficients of interest are implicitly being divided by an unknown variance term that we can never recover. So what do I mean by that? Well, we can rewrite this u tilde 1, as the difference in the betas plus gamma times the difference in the z's, and the difference in the betas is multiplied by x. So we can rewrite this as beta tilde times x plus gamma times z tilde. But in essence, or in actuality, the beta tilde is actually some beta star divided by sigma, and we will never know what that sigma is because of this scale invariance property of utility. And then same with this gamma star and sigma. So we'll never get to estimate beta star or gamma star, because we'll never know what this sigma is that it's being divided by. And again, this contrasts with linear regression models where we can easily estimate the sigma. And why does this need to be different? Well, because linear regression models, we have a continuous y variable, but in a discrete choice model, we have a categorical outcome variable or dependent variable. And so since we have less variation in the dependent variable, that's going to limit what we can infer from correlations between x and the dependent variable. So let's also think about what this division by an unknown sigma implies if we're just looking at a regression table. So what I'm showing on the screen here is a regression table that you'll see in a lot of different scientific papers. They're basically adding more covariates to their models and then seeing how the coefficients change, as well as how the R-squared changes. So in a Logit model, we use the pseudo R-squared, not the actual R-squared, because it's not a continuous outcome variable. And we can see that the price is changing. So the price is getting closer to 0 as we add these additional covariates. The R-squared is also increasing, the pseudo R-squared. And so the question is, well, can I say that the effect of price on this utility maximization condition is that effect getting smaller as I add more controls? Well, the answer is we just don't know, because each of these controls, we can't compare the numbers in column 1 with the numbers in column 2 or column 3, because each model has its own sigma that it's implicitly being divided by. And likely the sigma is getting smaller as I go across the columns because the pseudo R-squared is getting bigger. We can't be sure of the relative magnitudes of each, but for this reason, we can't just say that price has a lower effect on the choice in column 2 than column 1, like we would if it was a linear regression model. So this is important to think about when you're interpreting the actual results of a discrete choice estimation problem. And for these types of comparisons, if you want to make them, you need to be using marginal effects, not the actual coefficients. Once you do the marginal effect, it will take into account this unobservable sigma, and so you'll be able to compare apples to apples at that point. So this framework has formed a foundation through which we can now start to think about what is the exact formula for the probability of making a choice, as well as how would we take this to data and actually estimate parameters that represent preferences. We'll talk about those topics in the next set of videos.